Howdy. We're ready for chapter 5. Let's do a little more practice in it. And so today we'll be dealing with gas laws for the most part. And these problems tend to be word problems and they give us a lot of trouble. So one of the main things we want to break down is this idea of what is given versus what they want. And learn to break down a word problem into these categories. And then let's say they tell us something like 35.0 milliliters. We need to be able to recognize the units and the symbol that goes with that. So if it's milliliters, it'll be volume, and so that'll be a V. If we see something that has ATM, that'll be a P. If it's degrees Fahrenheit, that'll be our temperature. And so learning to recognize these things is going to be the key to this chapter. All right, and most of the rest of the chapters. So it's a very important skill. So let's start with some chapter 5 problems. And so the first one up, scary looking problem here. So let me pull it up full screen here. Which of the following is not a postulate of the kinetic molecular theory? All right, so this was just explaining the behavior of gases and molecules for an ideal gas. So first, the molecules of a gas move rapidly. Sure, they were random straight line motion. Okay. They collide with each other. The total energy of the molecules before the collision is the same as their total energy after the collision. That's an elastic collision. That's actually true. We didn't really cover that, but that's fine. Molecules of a gas are strongly attracted to each other. Now, the idea was that they bounce off of each other, and that can't be true if B is also true. All right, so if they were attracting each other, they would actually mess up their total energy. Molecules in the gas are tiny compared to this between them. Absolutely. We said the molecular volume is insignificant compared to the space between them. So C would be our answer for the wrong one, which one is not part of kinetic molecular theory. Okay. Let's look up here again. So then we've got a next series of questions. So this series of question here, when I look at it, it tells me right away there's no numbers. This is a concept question. This is really just identifying which question. So what we want to look at is which things are being held constant, which things are changing. And so when I see constant temperature, that means I don't even have to worry about temperature. The volume of the gas varies inversely with its pressure. So really all I care about, so notice it said given amount, that means the amount of gas, the moles doesn't change. So the only thing changing here is volume and pressure. So pressure and volume, that was Boyle's law. All right. So make sure you can identify which gas law is which. So the next question, we see a lot more going on. It's a longer looking one, but we see some numbers. So let's go ahead and break this one down. So I've got a gas enclosed in a cylinder fitted with a piston. The volume of the gas is, so I'm going to start with my given. All right, and so the volume of the gas, I've got 2.00 liters. I've got 1.00 ATM. And then it said something about 6.00 liters. And it says, what is the value for the pressure of the gas at this new volume? So what they want is pressure. All right, so once I've identified these things, the next thing I'm going to do is come in and I'm going to label these with this symbol. So the symbol for liters, that's going to be volume. I'll put a V. Atmosphere is pressure. Liters is volume. And then I've got another pressure over here. So I've got two pressures and two volumes. All right. Now the next thing we want to do is go ahead and figure out which things go together. So I need to read this question again. I've got two different volumes and one pressure that were given to me. So I need to decide, does this 1 ATM go with the 2 liters or does it go with the 6 liters? Well, it goes with the 2 according to the problem, so I'm going to label those two as V1 and P1. You'll notice I don't care about this idea of before and after. It doesn't matter. I just need to show that these two go together and these two go together. And so that's where my 1s and 2s for my subscripts come from. Just keeping track of what goes together. Now I could identify based off of volume and pressure that again this is Boyle's law. Or I could start with my ideal gas law, PV equals nRT, and then pressure and volume, and so I can just derive it from these. So 1s and 2s, P1 V1 equals P2 V2, and we want pressure 2, P1 V1 over V2 equals P2. All right. Now, we want to make sure everything's in the right units to cancel out. A good way of checking that is our units for R, and so it was in atmospheres times liters over moles times Kelvin. All right, remember that's on the back of our periodic table if we ever forget where it's at. And so everything looks like they're in the right units, so I can go ahead and plug them in. We can plug in the units real quick, just double check that they're going to cancel out. I'll have atmospheres times liters over liters. Notice the liters cancel out. Alright, so liters cancel out, we're left with atmospheres, which is what we want for the pressure. Alright, so just got to plug in the numbers here. Let's see, we got 1.00 times 2.00 divided by 6.00. 26 is 1/3. Alright, and so that's my pressure, so 0.33 repeating ATM. Which would be D on this problem. Okay, so if I'm not sure on these, I can also go refer to a file that we have called our helpful equations, and it's got 2 parts. All right, so helpful equations part 1 and part 2. So get a little closer so we can see it. And it's got all these listed out. So I just find the one that has 2 pressures and 2 volumes. And so that's easy enough. All right. So this problem, not too difficult once we get it out of word problem form. And the key is you start to see that these are very similar when we have our broken down and have our symbols for the equations written in there. All right, so let's go to the all right, and this one says the statement that the volume of a fixed amount of gas at a constant pressure is directly proportional. We could memorize it directly and then inversely. That's fine. All we got to really worry about on this one. So fixed amount, that doesn't change. Constant pressure, that doesn't change. So this is volume and temperature. So volume and temperature was Charles's law. All right. So that one is identification. It's pretty much memorization. So this one we're going to assume is Charles's law, but we don't know for sure. Let's check it. So they said we take a balloon, we fill it up at minus 40 degrees Celsius, and it had a volume of 2.00 liters. So I'm keying up on any kind of numbers, and then it said the pressure remains constant, so that means I don't have to worry about it. What is the volume of the same balloon? If I take it inside and it's 25 degrees Celsius, and it wants to know the volume. So what they want is volume, what they gave me. So I'm going to make my list. Let's see, I've got temperature, I've got volume, I've got another temperature, we got another volume. All right, so minus 40 and 2 liters, those went together. So I'm going to put 1s and 2s for the others. All right, now I want to double check everything's in the right units. One thing students miss a lot is they forget and use Celsius instead of Kelvin. So all my temperatures need to be in Kelvin. So K is equal to C plus 273. This is multiple choice. I'm not even going to worry about the 0.15. So 273 minus 40. Oh, that's easy enough. That's 233. Let's go ahead and knock that out. 233. I'm just going to write it up there so I have it for later. I'll put my units, K. 25, that would be 298 K. Volume should be in liters. All my answers are in liters, so we're in good shape. Now I could refer to my sheet. It has one that says T1 V1. T1 over V1 equals T2 over V2. Or I can start here. We're looking at volume and temperature. So if I'm solving this, I'll have V1 over T1 equals V2 over T2. And then you plug it in. I can solve it, or I can plug it in right now. I'm going to go ahead and plug in right now. We'll do 2 over 233 equals, I'll put in X so we can do our algebra. And then the T2 on the bottom was 298. So 2 times 298 divided by 233. I'm going to cross multiply and then divide. So doing a couple of steps there. So let's do 2 times 298 divided by 233. 2.56 or 2.6 if they only use 2 sig figs, which is A, 2.6. Okay. So you can bet that whatever the answer would, if we had used Celsius, you can bet that's going to be on there. All right, so gotta always be careful about that. All right. So the next one says use the ideal gas law to calculate, and it gives us a bunch of stuff. Now, let's say they didn't tell me use the ideal gas law. Let's just write down what's given, and we'll see if we could figure it out. So 0.200 moles of nitrogen gas at 1.00 atm and 27 degrees Celsius, and it asks for the volume. This is what it wants, is the volume. All right. So moles is my symbol N, atmosphere is pressure, degrees Celsius temperature, and so you can see I have one of each. So I've got all 4 variables and one of each. So we usually call this a plug and chug kind of problem, but it's ideal gas law, just like they said. PV equals nRT. I'm going to divide both sides by P. So V is nRT divided by P. Now the problem is you got to put everything in the right units. So moles is fine, atmosphere is fine, and it tells me in the problem the value to use for R. And notice it's Kelvin, so I need to take this into Kelvin. 273 plus 27 should be 300. It is 300 Kelvin. So let's go ahead and plug everything in. 0.20821 300 divided by 1. So 0.2 times 0.0821 times 300. The volume should be 4.926. 4.9 will be fine for what they have. 27 degrees only had 2 sig figs, so we'll use 2 sig figs. All right. Okay, not too big a deal. Again, we'll just make sure you get used to making a list of what they give you and what they want. All right, that's the key to these problems. They're not as intimidating once you get out of the word problems. All right, it asks the next one, the standard temperature and pressure, the conditions for that. So STP, 1 atmosphere and 0 Kelvin. All right, so think of drinking something that has ice in it while you're sitting on the beach at sea level. All right, 1 atmosphere, 0 degrees Celsius. What did I say? 0 Kelvin? Oh no. So 1 atmosphere, 0 degrees Celsius. That's D. All right. Now 0 Kelvin. good way to keep it up is not that one. 0 Kelvin, it's really tough to get to. It's almost impossible for us to measure anything at 0 Kelvin because actually, whatever instrument we use to measure the temperature introduces heat. So very, very cold. So we're just looking at ice, which is 0 degrees Celsius, in 1 atmosphere. So 1 atmosphere, 0 degrees Celsius. All right. That would be 273 Kelvin if it asked for Kelvin. All right, so this one has N2, F2, and HE, and gave us those components. And it says 0.5 ATM. So let's write those numbers down. 0.16 ATM and 0.18 ATM. All right. So looking at these, you'll notice they're all pressures. And so if we are trying to figure this out, that's a giveaway that they're all pressures. Now, N2, F2, and HE, and we want to know which one's which, but we get that word respectively. And so that means that they're in the same order. So this N2 would be the first one, F2 is the second one given, and then helium would be this last one given. And it wants to know what is the pressure of the gas mixture. So I've got 3 different gases, 1, 2, 3, and it wants to know their pressure of the mixture. So we're going to be using Dalton's law of partial pressures. And it just says that the total mixture, you just add up the pressure for all of these. So 0.5 and 0.16 and 0.18. Alright, so there's 4 and 1 and 8.84 ATM. And that's B. Okay. So we just added these up. Maybe they had told me the total and all of them but one, then we would have just done a little bit of algebra. Not real difficult. Looks like a scary problem. It was actually just addition. Okay. So then let's go to the next one. It says, yelling at us, a balloon filled with helium gas at 1 ATM, so 1.00 ATM, and it has 15.6 liters. And then they give me a number 0.150 ATM. And we want to see what volume. Volume is what they're asking about. So I've got a pressure, a volume, another pressure, and we got another volume. So let's double check. 15.6, does it go with the 1 or does it go with the 0.15? And it goes with the 1. So those two will be P1 and V1, and this will be P2 and V2. So P1 V1 equals P2 V2. This is Boyle's law. All right. So then we just plug these in if they're in the right units, atmospheres and liters. Very good. So it's just 15.6 divided by 0.15 would be our new volume. And I got 104 liters. And so this balloon, we let it go and it went really high. And so you can see why balloons don't make it to outer space. They pop. They pop. So this thing really got 10 times bigger, almost. And so, really got bigger. All right. So not too bad. This one says we have an ideal gas. It has a volume of 5 liters. So let's start writing our numbers down. 5.00 liters at 50 degrees Fahrenheit. And it says what temperature, so this is what they want, temperature. And they want it in degrees Fahrenheit. So I'm going to go ahead and put a little note there. And it wants the volume to double. So if it's 5 liters, then it wants this to be 10 liters. So this would be doubling. So I have V1 and T1 and V2, and this would be T2 over here. All right. I need things in the right units. So we're going to have to go F equals 1.8 C plus 32. Now, if I don't remember that, it's down here on my list of helpful equations. So it's on part 2 of my helpful equations. That's from back in chapter 1. And then we'll have to K equals C plus 273.15. So I'm just going to take my parentheses, don't forget those. So 50 minus 32 divided by 1.8 will be my Celsius. 50 minus 32 divided by 1.8, I get 10 degrees Celsius. And then I'm going to have to add 273.15. So I've got my temperature here, right up here, that in blue is 283.15 Kelvin. So now when I'm ready to go plug in this in, make sure we plug in the Kelvin. So plugging this in, got to look up the equation, or I can start with my ideal gas law. V1 over T1 equals V2 over T2. Remember, if you flip both of these, as long as both the volumes are on the top or both are on the bottom, it's fine. The important part is you gotta be in Kelvin, or it's just not going to work. All right. So V1 was 5, 283.15. V2 was 10, and I'm going to put an X down here. Doing this algebra over here, I've got 5x equals 283.15, and so x will be 2,831.5 divided by 5, and this will be 566.3. Now that's going to be in Kelvin. Be careful. That's in Kelvin. They wanted the temperature in Fahrenheit. So to get that in Fahrenheit, I'm going to have to go back. All right, so I'll subtract 273.15 from that. And so that will be 293.15 degrees Celsius. And F equals 1.8 times 293.15 plus 32. Plus 32. 559.67 degrees Fahrenheit. So it takes a lot to double that volume. All right, so it takes a real high temperature to double the volume. And that was the same kind of thing that was throwing off Charles when he was first looking at this. He said, hey, if I double the volume, shouldn't the temperature double? You have to do it in Kelvin. So this one, a little bit tougher, actually much tougher than I would hit us with a book, but as long as you're paying attention to your units, and my advice is always change the units over before you plug them in. All right, so always double check your units. All right, so the last one here, it says a 5-liter balloon exerts a pressure of 2 atmospheres at 30 degrees Celsius. What is the pressure the balloon exerts if the volume is increased to 7 liters at 40 degrees Celsius? Right, a lot of stuff going on this one. We better jot it all down. 5.00 liters, 2.00 atm, 30 degrees Celsius, and then I have 7.0 liters and 40 degrees Celsius, and it wants to know a pressure. All right, wants to know a pressure. All right, so let's come through and label things. Liters is volume, atm is pressure, degrees Celsius it will be temperature, Liters is volume, degrees Celsius is temperature, and then we're doing pressure over there. All right, so I've got three variables, two of each. So this is the combined gas law. All right, three variables, two of each. So let's figure out which things go together. So rereading the question, 5 liters has a pressure of 2 atmospheres. So those two go together. I'm going to put ones for those. And it also says at 30 degrees Celsius. So all three of those went together, and then all three of these go together. So there's my ones and my twos. They don't always give them in that order, but they usually do. All right. So as long as I keep up with these, go together, and the others are separate. All right. So PV equals nRT, pressure, volume, temperature equals pressure, volume, temperature, ones and twos. I'm using some of the tricks we showed last time. So now a lot of people like to go ahead and do this algebra first. Usually the mistake they make is they then plug in for they plug T1 value into T2 and vice versa. All right. Before I plug anything in, I need to double check my units. So liters is fine, atmosphere is fine, degrees Celsius is not. So this would be 303.15 Kelvin. Liters is fine. Well, this is not right. So 273.15 plus 40, that is 313.15 Kelvin. All right, so now we can plug everything in. 2 times 5 over 303.15 equals, I'm going to put my X, my volume 2 was 7, and then I've got T2 is 313.15, cross multiply, so 10 times 313.15 equals X times 7 times 303.15. Then I'll divide both sides, so I've got 10 times 313.15 divided by 7 times 303.15. Now I'm going to go ahead and add extra set parentheses there. A lot of people forget those. So 10 times 313.15 divided by open parentheses 7 times 303.15. Close my parentheses if I want, or just hit enter. And I got 1.48 is X. Let's double check my units. So P1 was ATM, volume 1 was liters, T1 was Kelvin. On this side, our X, we had liters, and we had Kelvin. Alright, so Kelvins are going to cancel out, liters are going to cancel out. I'll get 18. And does that make sense? We increased the volume, but we also increased the temperature, so the pressure went up, went down a little bit. Yeah, okay, because the volume almost went up by quite a bit. Okay, so all right, there's our answer, and that's the key to this stuff, is to kind of learn, break things down, get out of the word problem, get all those words out of your way. You're looking for some keywords. You're looking for respectively, that's important. You're looking for anything that has units, any number you probably want to jot down. You're looking for something that says being held constant. That's usually a good sign that you can ignore it. All right. And so it's really just a matter of getting used to figuring out which units go to which symbol. And then once you have the list of the symbols, finding them on the list of equations is not too difficult. All right. So that's the secret: is figure out temperature is in Celsius or Kelvin or Fahrenheit. Figuring out volume is going to be in milliliters or liters. Pressure will be in atmosphere or millimeters mercury. Um, or maybe they use torr. Okay? Now, the one that gives people a lot of trouble is if the problem doesn't give you moles, but instead it gives you grams. And in that case, you're going to have to use the molar mass to find the moles. So if it gives you grams, they're usually telling you N. All right. So practice chapter 5. It's really about working those problems. There's a little bit of memorization, but not much. All right. STP, um, and that's about it. The equations, you'll have your hopefully equation sheet. There's the gas laws are on there, but I don't tell you which one's which. So you need to keep up which gas law is which. All right. So we went over all that last time. You can do it. Just remember to break it down one step at a time. Don't get overwhelmed by the entire problem all at once. All right. Catch you on the next one.